In this next problem, I have a car that's traveling due west with a momentum of 2.1 times 10 to the power 4 kilograms times meters per second. And then it heads due north with a different momentum. And then our goal is to find the car's change in momentum here. Okay, so remember, a change in momentum, we can label that as delta P. And that's really equal to your final momentum. And then you can subtract your initial momentum. Now, since the change of momentum is a vector, let's go ahead and set up a vector diagram here. And if I'm looking for my final momentum vector, we can look at this part of the problem here where it's going due north with a momentum of 2.8 times 10 to the power 4 kilograms times meters per second. So if I want to draw a vector for that, it will look like this. So here's a vector going in the north direction. So this right here is my final momentum vector there. And that has a magnitude value of 2.8 times 10 to the power of 4. Now if I go back to my change in momentum formula here, I need to subtract my initial momentum vector here. So I got to subtract the initial momentum vector. Now initially we're going due west. All right, so if we want to create a negative momentum vector here, we just go in the opposite direction, which is in the east direction now. Okay, so if I go ahead and set up a vector for that, here's a vector going in the east direction here. And that right there is my initial momentum vector going in the opposite direction, right? So that's negative P naught. And that has a value of 2.1 times 10 to the power of 4. Okay, so that's how you can set up your vector diagram there. And then if I connect create a resultant vector by connecting the vectors from head to tail, my resultant vector will be right here in purple. And that right there is my change in momentum, right? So I need to find the magnitude right there of the change in momentum, and I also need to find the direction right here of because a change in momentum is a vector quantity. Okay, so let's go ahead and find out what delta P is, the magnitude of that, and then we can find the direction right after. Okay, so since this is a right angle triangle, I can use the Pythagorean theorem here. So I can say that the change in momentum squared is equal to the magnitude of my my final momentum, and then I can add that to my initial momentum, and I can square that. So there's the Pythagorean theorem right there. And let me just continue the line here. So this is delta P squared equals 2. So the magnitude of my final momentum is the magnitude of my final momentum vector is 2.8 times 10 to the power of 4. And I square that. And then I can add that to the magnitude of my initial momentum vector, which is 2.1 times 10 to the power of 4. And then I can square that. Okay, and then from here on, you're off to the calculator here. So delta P squared equals 2. And if I go to my calculator here, I get 1.225 times 10 to the power of 9. And after that, you definitely need to square root both sides. And then I can find the magnitude of my change in momentum, which is about 35,000. And then my units are kilograms times meters per second. If you want to use scientific notation here, that's 3.5 times 10 to the power of 4, and that's kilograms times meters per second. All right, so there is my magnitude in the change in momentum. And after that, I also need to find the direction there because a change in momentum has both magnitude and direction. So if I go back to my triangle diagram right here, I want to find this particular angle right there. Okay, so if I go straight across here, I have my opposite right here. If I go right next to that angle, then I have my adjacent over here. So I have my opposite and my adjacent, and what that means is I can use a tan ratio. So tan of the angle equals to the opposite over the adjacent. So the opposite is going to be 2.1 times 10 to the power 4. And then I'll divide that by my adjacent, and my adjacent here is going to be 2.8 times 10 to the power of 4. Okay, so if I go to my calculator here again, I get tan theta, and if I divide those two numbers, we get 3 divided by 4. And then finally, our angle here is going to equal to the inverse of tan, and then let's write in 3 over 4, and then our angle value here is we get 36.87 degrees, and this is in the east of north direction here. East of north. Okay. So if I go back up to my diagram right here, so let me just kind of go ahead and just draw a few more signs here. Right, so this is in the east direction, that's the north direction there. So what we've just found here is this angle right here is going to be a 36.87 degrees, and we're going in the east of north direction there. Okay, so just to kind of summarize this problem here, here's my magnitude for the change of momentum, which is 3.5 times 10 to the power 4 kilograms times meters per second. And here's my direction right there, 36.87 degrees east of north. And there is the vector diagram above. Let's take a look at another vector calculation problem. And for this question, we have a 12 kilogram shopping cart that rolls due south at 1.5 meters per second. After striking the bumper of a car, it then travels at 0.8 meters per second, and the direction is 30 degrees east to south. And we want to figure out the magnitude of the change in momentum sustained by the shopping cart. Okay, so there's a lot going on in this problem here. Since we want to find a change in momentum is delta P, which equals to your final momentum minus your initial momentum. Okay, so let's go ahead and figure out what's going on initially in this problem. So initially, the cart here is 12 kilograms. And its speed is 1.50 meters per second. And if we go ahead and find the momentum here, momentum is just mass times the speed here, which is 12 times 1.50. And if we calculate that, the momentum that we get here is going to be 18. And the units are kilograms times meters per second. And the direction here is going to be in the south direction here. Right, so that is your initial momentum right there, 18 kilograms times meters per second in the south direction. Okay, after that, let's see what's happening once we let's see what's happening after we strike the bumper of a car. Well, the mass is still going to be 12, but now the speed is now going to be 0.8. And let's go ahead and find the final momentum there, the magnitude of that, which will be 12 times 0.80. And then our final momentum here is going to be 9.6 kilograms times meters per second. And we're going in this 30 degrees east of south. Okay, now let's go ahead and figure out what's going on with this change in momentum here, which is really your final momentum minus your initial momentum. Okay, so since we need to deal with our final momentum first, let's take a look at this 9.6 kilograms times meters per second in the 30 degrees east of south direction. Okay, so if I'm going in the east of south direction here, if I go ahead and draw a vector diagram here, that kind of looks like this. It's going in this direction. Whoops. Let me get a brand new marker here, and let's just draw a vector like that. So that right there is kind of like in your east of south direction there. Okay, and we'll call this your final momentum vector here, and that has a value of 9.6. Okay, and then if I go ahead and just put a dot there and just put the angles in now. So what we're trying to say right here is the 30 degrees is actually right here, just below like that, 30 degrees like that. Okay. And then after, if I go back to my change in momentum, I need to subtract my initial momentum vector. Okay, so initially I'm going in the south direction, right? So if I want to subtract that, the opposite of south is actually going to be in the north direction. Okay, so going to my diagram here, I want to draw another vector here going in the north direction here, and I'm going to label that like that. And that right there is my negative momentum initial vector right there, and that has a value of 18 kilograms times meters per second there. And our goal now is we want to find the change of momentum, which is really the resultant vector right here like that. So that right there, that is the change in momentum, and I'll label that delta P. All right, so our goal is we want to find the magnitude of this vector right there. Okay, so there's a few things that you have to kind of recognize for this problem here. Let me just erase this here. Now, if we know this is 30 degrees below there, if this is 30 degrees right here, then that means this is also going to be 30 degrees. Okay, so we have the alternate interior angles there. So 30 degrees is also in this bottom corner like that. Okay, so once we know that, then we can set up the cosine law here, because we're given 9.6 and the 18. So if I just kind of erase this a little bit more now and say that this is going to be a 9.6 and we have the 18 there, we can definitely find the delta p there, right? So if I want to set up an equation to solve for delta p, we're using the cosine law here, where delta p squared is equal to the magnitude of your final momentum vector plus the magnitude of your initial momentum vector minus 2 times the final momentum vector times the initial momentum vector times cos of the angle. And the angle that we're dealing here is going to be 30 degrees. Okay, so there's your cosine law right there, and all we have to do here is just kind of plug in the numbers here, and then we can find the magnitude for our change in momentum here. So our final momentum here is going to be 18. So I square that. Our initial momentum here was 9.6, the magnitude that is, minus 2 times 18 times 9.6 times cos of 30 degrees. And then from here, we're pretty much off to the calculators now. So our change in momentum here, and the right-hand side is going to equal to 116.862. And then we can square root both sides. And then the magnitude of the change in momentum here is equal to 10.810 kilograms dot meters per second. And if you want to round this up to the next nearest number here, that'll be 11 kilograms times meters per second. And we can stop there because this question is only looking for the magnitude here. So if I go back to my options here, I guess option C would be the best answer here. In this next problem, we have a 0.25 kilogram ball moving north at 7.7 meters per second. Then it strikes a wall and rebounds heading east with the same speed as 7.7 meters per second. And we want to figure out the magnitude and direction of the impulse on the ball there. Okay, let's go ahead and collect some information here. So we know the mass is 0.25 kilograms, and we know the speed is 7.7 meters per second. So let's go ahead and find the magnitude of the initial momentum here. So that's going to be 0.25 times 7.7, and if I multiply those two numbers together there, the magnitude of the momentum here is going to be 1.925. And then the units are kilograms times meters per second. And we know that this is also going in the north direction there. So let's just put north like that. Okay. And it also turns out that the final momentum here can also be calculated pretty quickly, because the question pretty much states that once we hit the wall, we rebound with the same speed. All right. So if we have the same speed, and if the mass is 0.25, then the magnitude of the final momentum is also going to be 1.925 kilograms times meters per second. And this is actually going in the east direction. Okay, so if I go back to the problem, it does state that the ball is going in the east direction after hitting the wall. Okay, and once again, we want to find the magnitude and direction of the impulse on the ball there. Okay, so now that I have some information there, let's go ahead and start solving the problem here. So we know that impulse is equal to a change in momentum. And a change in momentum, we've seen this a few times already in the previous problems, but it's really your final momentum, and then you want to subtract your initial momentum. Okay, so let's go ahead and set up a vector diagram here, starting with the final momentum. So our final momentum here is going in the east direction there. Okay, so if I go ahead and use our red marker here, all right, so here is a vector going in the east direction here. All right, so that is the final momentum vector. And and that has a magnitude of 1.925 kilograms times meters per second. And then we want to subtract the initial momentum vector. Now initially we're going north, and if we want to subtract that, that means we are going in the south direction. Okay, so if I create a vector for that, we just draw a vector going the south direction. All right, so that is minus p naught, which is the vector of the initial momentum there, going the opposite direction. And that also has a magnitude of 1.925. And now we want to find the magnitude and direction of the impulse, which is the change in momentum, which is essentially the resultant vector right there. So that right there is delta p. Okay, and just like the previous problems, we can create a right angle triangle, and essentially to find the magnitude here of the change in momentum, we are using the Pythagorean theorem again. So delta p squared is equal to pf squared plus your initial momentum squared, and then from here let's plug in the numbers here, which is 1.925 squared plus bracket 1.925 squared, and on the left hand side I have my change in momentum to the power 2. So this will help us calculate the magnitude of the impulse here, and so I have delta p to the power 2, and that's going to be equal to 7.41125, and then we can square root both sides, and the momentum here now, the change in momentum is 2.722 kilograms times meters per second. Okay. And remember, impulse also has the units newtons times seconds there, so these are all equivalent forms there. And in order to find the direction now, okay, so let's just kind of highlight this vector right here. We've just stated that that magnitude of that change in momentum is 2.722. So momentum and impulse are the same thing. And now we want to find the direction as well, so we've got to find this angle as well, right? So over here, this is the opposite. And right next to this angle, we have the adjacent, right? So when we have opposite and adjacent, we can use tan of the angle. And the opposite here is 1.925. And then we also divide that by 1.925. And looking at the ratio there, the numerator and the denominator are the same. So this is really tan theta equals to 1 there. And then if I find the inverse tan here, we can write this as tan inverse, and then 1 inside the brackets there, you do get an angle of 45 degrees. Okay, so if I go back to my diagram now, this is really 45 degrees here. All right, and basically since it's 45 degrees, you can say south of east or east to south. It doesn't really matter because it's 45 degrees there. Okay, so once again, the magnitude is 2.7. and the direction will be 45 degrees, and this is going in the south of east direction there. Or you can say east to south. It really doesn't matter when you have 45 degrees there. So if I go back to my multiple choice options here, these look like good options for the magnitude, and this looks like a good option for the direction here. So the best answer here looks like option D. Okay, so that concludes this video guide for this part of the homework.